linear/ordinary least squares regression. With correlation, we were concerned with the relationship between X and Y. Is X related to Y? Is there an association between X and Y? You'll also remember that when we did the scatter plot, we used a line through all of those points to demonstrate how close those points were. So we'd have coordinates for an observation, and they had an X coordinate and a Y coordinate that would represent a point on the scatter plot. We had that for every observation, and then we drew a line of best fit through those points, and that was the regression line. Now we're taking our knowledge of that correlation, our knowledge of that line, the best fit between points, which represents a relationship between two variables, along with our knowledge of algebra to help us start predicting values of the Y variable. So whereas in correlation, we were concerned with, is X related to Y? We knew the Y variable was our outcome variable, the X variable was our predictor. We were only concerned with, is one related to the other? With regression, we're saying, if you give us all the X information, can we predict values of Y? More appropriately, I should say, if you give us all the information, the X and Y characteristics for every observation, can I create a predicted Y value based on that information? So that's sort of what regression is doing. It's taking all of the other points and saying, given your case, where would you fall in these data? So we can use values of X to predict values of Y. And remember that that line of best fit is our best guess for values of Y. The clearest illustration would be in correlation. We saw that line of best fit between two interval ratio variables. With correlation, we had an X variable that was interval ratio, a Y variable that was interval ratio, and that regression line just went through those points. But that same logic of using X to predict Y can be extended to other kinds of levels of measurement. So we can have a nominal or ordinal predictor with an interval ratio outcome. That would still be a form of regression. Nominal ordinal predictors, so more than one predictor and an interval ratio outcome. That is also still regression, known as multiple regression. We have an extension of those types of regressions with nominal and ordinal predictors, as well as nominal or ordinal outcomes. And this is known as a logit family or logistic regression. So all of these are forms of regression. We're using information from the data of X and Y to predict values of Y. So if somebody just randomly gave me an X value, I could predict their Y value based on all of the other information that I have from all other XY pairs. If we wanted to draw a straight line through some points, that line of best fit, we remember that equation, right? Y equals mx plus b, where Y is the outcome variable, X is obviously the X variable. M here represents the slope associated with that X variable. So this would mean for every 1 unit change in X, Y changes by M units. And then B here is the value of the intercept, or the value of Y when X is equal to 0. However, that same equation in many textbooks is rewritten as Y equals A plus BX. Here we replace B with A, we replace M with B. So Y equals A plus BX. Again, A is the intercept, B is the slope. However, we also know that we're trying to predict the value of Y. That line of best fit goes through all the points of Y, and that's our best guess for any value of X. If we recall, that scatter plot would have a bunch of different points and the line would cut through it. The perfect correlation would be one in which all of those points fall on that line, but that rarely happens in real life. We always have some distance between the actual XY coordinate and the predicted Y line. That line represents the predicted Y value for any given X. So there will always be some distance between the actual Y value and the predicted Y value. These are known as residuals, the distance between an XY coordinate and the line at that X coordinate, the vertical distance between the Y coordinate and the predicted Y value. So we rewrite the equation as Y equals A plus BX plus that residual, some error. The actual Y value for any given coordinate will be the slope of that line plus some error. Or we can just get rid of the error term altogether and say, we're not giving you actual values of Y, we're giving a predicted value of Y. So we move it back to Y equals A plus BX, but it's a Y hat. So Y hat is the predicted value of Y at any given X. And then finally, we change that A to a B value. B sub 0 is going to be our intercept. Everything's expressed in slopes and intercepts. We have a B0, that's the intercept. Instead of BX, we have B1, X1. And we do that because we want to create a situation that allows for more X variables and their associated B slopes, the regression coefficients. B1 here is the slope associated with the X variable, the X1 variable. For every 1 unit change in X, there's a B unit change in the predicted Y value. x1 is that first x variable. Looking at this equation, you'll notice we still only have one y value and one x value. This would indicate a bivariate relationship here between two variables. We have xy coordinates, we have an intercept for that line, and a slope for that line associated with the x value. So this would be a bivariate regression line, also known as a simple linear regression. Very rarely do we use simple regressions. Simple regressions are usually just to draw that line that cuts through the correlation on a scatter plot. So it's called simple linear regression, but why is it called ordinary least squares? So we're still in simple land, in X and Y land, bivariate land. So we have this scatter plot looking at advertising budget in thousands and album sales in thousands. We see that as advertising budget goes up, album sales also goes up. So we have a positive relationship. The blue dots represent the XY coordinates for each observation, the values for each observation. So this case here would be the advertising budget for maybe that band is about $1,100 or $1.1 million and 300,000 album sales as the outcome. Same for this, right? We can do 1.5 million and 365,000 album sales. That green line in between all of those points is the line that is best fit for our data. It's the line that cuts across all the cases. And we call this the best fit line because it is the one that minimizes the distance between all of those points and the line. Or put another way, it uses all the X and Y coordinates to create a line that comes as close as possible to all of those points. We could easily draw a line that is something like this, right? If we wanted to cut off the data just right here. That line would extend, and while it would be close to all the points here up at the top end, it would be really far, like if we extended this line all the way out this way, it'd be super far from all of these blue points here. Close to that one, really far from this one, really far from this one, super far from this one, and further and further and further. We want a line that's gonna come as close as possible to all of the points. Again, that line is going to be the intercept plus or minus the slope times whatever the x value is. You'll notice that only certain points fall on the line. This point is kind of on the line, but it's still off. This point is close to the line, it's off. This point down here is close to the line, but it's off. So none of these points actually fall on the line, but it does represent the line that is best fitting for the data. The reason why we select this line is because we want a line that minimizes the sum of all of those spaces, the sum of all the residuals. A line that is best fitting is one that makes those distances, those dash red lines, as small as possible. So here we have the coordinate xy. So this is the actual values, observed values for someone. Here is the same x value, but their predicted y value given all of the other data. So predicted y. This area here is known as the residual. The residual is the error, the y value minus the predicted y value. And again, the best fitting line is one that minimizes those residuals. But if we summed up all those residuals, this distance, this positive plus this negative, 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 you'll notice there are only a few positives, a bunch of smaller negatives. When we sum up all those distances, it's going to sum to 0. Much like when we're summing up the deviation scores for each person, they're going to sum to 0 because the mean represents the center of gravity. Here, the best fitting line also represents the center of gravity, distances between each of these points. So instead of summing up all those residuals, we sum the squared residuals. The best fitting line, the line of best fit, the regression line through these points is one in which the squared residuals are minimized. The line here is one that minimizes, so least, the squared residuals, squared. This is why we call it ordinary least squared. It is a linear line that minimizes least the squared residuals, ordinary least squares. I will always refer to this as OLS regression. All right, back to this simple linear regression model. We know that B sub 0 is the y-intercept, the point at which the regression line crosses the y-axis. B1 is the slope for that x value, x1, is the regression coefficient, the amount of change in y for each 1 unit change in x. It also represents the direction and strength of that relationship between x and y. That slope for each x variable is the covariance between x and y, so how much they're moving together, they vary together, divided by the variance for x. So how much are they moving together over how much does x move by itself? So this is the slope calculation for the first x variable. The intercept calculation is pulled out this way. This B1 coefficient, because it's based on the covariance over the variance of x, we know that it's similarly related to the correlation coefficient. So we've been talking about this regression line as a line that cuts through a relationship between x and y, which is a bivariate relationship. And we're usually talking about a correlation relationship. Regression itself as a technique is helping us to predict values of y rather than just looking at the relationship between x and y. So in the social sciences, oftentimes we're interested in understanding not just how two things are related, but we do want to understand how can we predict values of y. So regression would fit perfectly. There are certain criteria we have to meet to ensure we're getting closer and closer to causation in the absence of an experiment. So if we want to get closer to causation, we must meet 3 criteria. First, if we want to look at causal relationships between x and y, meaning not only is y predicted by x, but x causes y, x must precede or come before y. If we're saying x has an effect on y, it has to come before. If you're saying that x causes y or causes a change in y, but y happens first, how can x cause anything? So x must precede. Second, you have to establish an association between x and y. So you can't say x causes y if they're not even correlated with one another or related to one another. If there's no association, you can't say that it's causal. You have to first meet the criterion of association before you say that something can cause something else. And finally, probably most importantly, we've been talking about these bivariate relationships, x related to y. But if we want to get closer to causation, we need to control for other factors. And if we think about what's going on in experimental designs, experimenters are controlling for all of these other factors, and the only thing, quote unquote, causing a change is the thing that they manipulated. So you have independence of observation, so you can't say that their group membership is what's causing some change. You randomly assign them, so you're adding an extra layer of removing bias. And the only thing that differs for any of these people is that one group is getting a manipulation and another's not. So they're controlling for everything else. Presumably, you're controlling for all of those things by randomly assigning and randomly selecting. So only the manipulation can be the thing that caused the outcome or change in the outcome. It's hard for us to do that if we're not running an experiment, but we do know the logic is they're controlling for all of those things. How do we do that in the social science in the absence of an experiment? We control for things. This third criterion is we need to ensure that this relationship is absent of spuriousness, meaning that we also must investigate whether or not x and y still have a relationship in the presence of other x variables, that the relationship between x and y can't be accounted for by other x variables. So I gave the example many weeks ago about the relationship between an x variable, shoe size, and a y variable, reading comprehension. And researchers found that there was a strong association between shoe size and reading comprehension. Is this a causal relationship? There's no face validity to the investigation. We know that x comes before y. We know that there's an association, but can we say that it's causal? Probably not, because we would have to test other variables to see if the relationship between shoe size and reading comprehension still exists. We can easily throw in a third variable that would explain that relationship, which would be age. Age could explain growth in shoe size, but also increases in reading comprehension. That is some external third variable that would explain the relationship between x and y, such that when you threw the third variable in, x number 2, the relationship between shoe size and reading comprehension disappeared. And now the relationship is between age and reading comprehension. So what we do if we want to get closer to causation is we have to throw in a third, a fourth, a kth variable that could account for the relationship between x and y. And the logic here is that if you throw in all these variables and the relationship between x and y still exists, you're getting closer and closer to causation. Not just any variables, but variables that presumably can affect the relationship between x and y, or something that's related to x and something that's related to y. We also need to think about the idea of parsimony. Do we throw in just a third variable? Do we throw in a fourth, a fifth, a 10th, a 15th? Well, what about a 30th and a 50th and a 100th variable? At what point do we say it's too many variables to be throwing in? So we have to include several other x variables. These are additional independent variables, also known as control variables, right? You want to control for those external factors to ensure that they can't remove or diminish the relationship between x and y. By including these multiple control variables, we are able to measure multiple competing variables that could represent different competing theories or hypotheses about the relationship between X and Y or about the impact on Y. I always use the example of protest participation. If I want to run a regression on the number of times somebody went to a protest event, I could easily say, well, maybe liberal individuals are more likely to go to protest events. So I run a model and I throw in the X variable conservative to liberal scale. So higher scores would represent being more liberal. And I find, yes, being more liberal is strongly associated with the number of protest events people went to. But we can't quite say that that's a causal relationship because there are different competing theories about why people protest. Some of those theories include, I had time, I wasn't working, I don't have obligations at home, a wife and kids and things like that. Those are known as biographical factors. Those factors might also play a role. So let's say I measure 3 additional variables to encompass this idea of biographical availability, whether or not they work full-time, whether or not they have a spouse, whether or not they have a kid. I throw those variables into it, and then all of a sudden, this measure of liberalism diminishes to non-existent. It's no longer related to a protest count. What that means is there was significant overlap in these 3 variables I just added and the liberalism variable. We're adding those controls, these competing theories to see, does mine still hold out? And in this example, it did not hold out. My liberalism theory did not pan out. And then by adding these multiple control variables, we're able to control for spuriousness, these unexplained 3rd, 4th, kth variables that could explain the relationship between X and Y. So now, instead of y hat equals b sub 0 plus b sub 1 x sub 1, we add all of these additional variables. So a slope for x2, a slope and x3, all the way through a kth variable, a slope and xk. Now that we have multiple controls in our model, it is no longer called a simple regression. It is now called a multiple regression. In most cases, when people are talking about ordinary least squares regression, we're talking about a multiple regression. This equation here would represent one full multiple OLS regression model with, it says M predictors here, it should say K predictors. Here I say B sub I, so this is going to be the B for a given X variable. So we have this intercept, then we have the first X variable, we have the slope for that one, slope for the second one, slope for the third one, and up to 8th variable. All right, the logic is that it runs essentially 2 tests. It runs multiple t-tests for each variable, and it runs an overall test. For each x variable, it examines how much each differ from 0. So if we go back, each x variable has an associated slope in an x. And what the regression equation does is it tries to assess, is this b value for this first x variable significantly different from 0? Same thing for b2 for x2, and same thing for b3. It compares our b, our slope, to an expected b in the population. And the expectation is similar to the logic of a chi-square. We would expect no relationship, no slope. So what it does is it calculates a t-statistic for each slope, which measures the variability between the b in the sample and the expected b in the population, divided by the variability within our own estimate of the b. So it's running tests for each b value, each slope. If this b is significantly different from 0, then we reject the null that b is equal to 0. Thus, for this variable, the slope is significantly related to the y variable. So if you're running a multiple regression with 10 x variables, you're going to have 10 different t-tests going on, clustered within the overall model, adjusting significance levels within the overall model, much like a Bonferroni alpha adjustment would do. Secondly, outside of running a t-test or significance test for each x variable, the regression model runs an overall test, an omnibus test for the model. The regression model also examines how much variability in y is explained by variation in the combination of those x variables. So not just running each x variable and seeing if their slope is significantly related to y, but saying overall, when we cluster all of these together, clump all these x variables together, does it significantly relate to the outcome or significantly predict the outcome variable? Specifically, what it does is it compares the null model, a regression model with no predictors and only an intercept, to our final model, our full model with all of our predictors. So it says, what does the model look like when it only has an intercept? What does it look like whenever we have all 15 of our variables in? Then it calculates an F ratio, an F statistic for the entire regression model, represented by variability in y as explained by x's in the regression model, divided by variability in y not explained by the x's. So we're trying to see how much more are our x's explaining than not. If this F ratio is significantly different from 0, we reject the null, and the null is that the null model is the same as our full model. So if we reject that, that means that our full model is so much better than no predictors at all. And in many cases, your final or full model will be better than the null model. Multiple regression, variable types. So you have multiple independent variables, and they can be any level of measurement. They can be nominal, they can be ordinal, they can be interval ratio. In the example we have in here, they're all interval ratio, just to make it easier for us to understand. And the dependent variable needs to be interval ratio. Bunch of assumptions. Dependent variable needs to be interval ratio. Independence of observations. We want to make sure that our cases aren't dependent on one another. What we're really trying to get at as independence of the error terms. There's no covariance between error terms and our X values. So independence of observations is a way of getting at that, or controlling for an independence of our error terms. We examine data collection strategy. We want to make sure that we're randomly sampling. Adequate sample size. Green, 1991. A large enough sample size is one in which we have enough cases at various values of the dependent variable for various values of the independent variable. Again, think of the large matrix of the attributes of the Y variable by the attributes of the X variable. And you want enough cases where you can adequately fill each of those cells. And if you don't have enough, then they're going to be variables that aren't adequately measuring some outcome variable. A good estimate is you want a total number of cases to be greater than or equal to 50 plus 8 times the number of independent variables you have. So if you have 10 independent variables, you want 50 plus 80, 130 cases. You want greater than or equal to 130 cases. This gets back to another issue that we were talking about earlier of how many variables are enough variables. You want a third variable to control for spuriousness. You want a fourth, you want a fifth. Okay, well, is that enough? Or do you need a sixth? Or do you need a 10th? Or do you need a 15th? Or do you need a 50th? At some point, it's going to become too many variables. And this is a good way of controlling the number of variables that you have in. If you need a 50th variable, 50 times 8 plus 50, you're going to need a lot of cases. But we want to think about this thing called parsimony. And parsimony is this idea that you want to explain enough of the outcome with fewer variables. We want to explain enough of the variance in the outcome, Y, with fewer numbers of variables. That means if we're explaining 50% of the variation Y with 10 variables and 51% of the variation Y with 100 variables, we have about the same explanatory power. So why include all those other variables? Normality, linearity, and homoscedasticity. Homoscedasticity is the same thing as homogeneity of variance that we saw with ANOVA. We want to ensure that the variables and their error terms are normally distributed, that they're linearly related, and that variances at all levels of the dependent variable are the same or similar at various levels of the independent variable. How do we see if we've met all these assumptions? Well, we could look at normality plots. We could look at a scatter plot to examine linearity, but we'd have to run a scatter plot for all of our variables. And we could examine a residuals plot or homoscedasticity. But by examining the residuals plot, we can actually see all of these things. We can see if we're violating normality. We can see if we're violating linearity as well as homoscedasticity. So we look at the points on the residuals plot. So each of those points represents these values on the X variable for a given predicted Y value. And we want them to fall on both sides of the predicted line. Absence of multicollinearity and singularity. Multicollinearity is this idea that two variables correlate too highly with one another. So what do? We examine the correlation matrix to see if any of the independent variables correlate at 0.9 or above. Basically, when you're throwing two variables in that correlate highly with one another, they're going to be more overlapped with one another than they are with the Y variable. And that could seriously screw up the explanatory power of these variables. Because if X explains, 10% of Y, and the other variable also explains 10% of Y, but it explains 90% of the other variable, there's so much overlap, all of their explanatory power is going to be washed out because it's eaten up by explaining values of the other X variable. So it gets all washed out of the model. So instead of including both of those, you select one and run that. Singularity is the idea that you're using the same thing in the model. Let's say you had like a marital satisfaction scale. And then you wanted to throw in a marital dissatisfaction scale. And all the marital dissatisfaction scale was a reverse code of the marital satisfaction scale. They would be so highly correlated, they'd be the same thing. They would be a negative correlation. So we'd likely find a 1.0 correlation between these two scales, but it would be a negative 1.0 because they're reverse scaled. In that case, you're using the same thing reversed. And when you throw it into the model, they're going to cancel each other out. It's saying you're running two of the same things. So you would choose one of those. Another version is using subscales. So you say marital satisfaction is measured as happiness in a marriage. So it's a scale of 1 to 10 on happiness and then 1 to 10 on this other thing. But then into the regression model, you throw in marital satisfaction is a range of 1 to 20. And then you throw marital happiness 1 to 10 and this other thing 1 to 10. These subscales are just subsets of the larger scale. So if you throw all three in, they're going to cancel each other out, right? And that's the idea behind singularity, right? You're measuring the same thing, one singular thing, 2 times. You can examine the correlation matrix and see if there's significant overlap in those things, or start thinking about the independent variables that you have in there. Are they just subsets of the same thing? Are they just reverse codes of the same thing, or are they different things? And then finally, absence of outliers. You want to make sure that the regression line isn't being pulled towards outliers, especially if you're modeling something like income, which always has outliers, right? It's going to be pulled towards those outlying cases. You can examine the scatter plots of each independent variable with the dependent variable to identify outliers, but you have to have extreme justification for removing cases. You don't want to seem like you're cherry picking data. Maybe you found a regression line that was really steep and you're like, oh, it's not supposed to be that steep. Seems like there's a high case up here. It might be an outlying case. Let me remove it. And then you remove it. And then it drops the regression line something closer to what you expected. You don't want to be doing that. So generally, what you do want to do is look at how the variable is distributed. If it's extreme, then you want to transform the variable. If not, then the likelihood is it's probably close enough to normality that you can proceed with the test. Multicollinearity and singularity. I have this example here. This is an example of a correlation matrix. You see everything on the main diagonal is removed, but if we saw a correlation between x2 and x2, it'd be 1. X3 and X3 would be 1, so on and so forth. So that's removed. The off diagonals are removed as well. But multicollinearity is that idea that you're seeing above 0.9 correlation between two variables. So in this case, we would see multicollinearity between X1 and X2, X1 and X3, X1 and X10, X2 and X3, X3 and X10, X8 and X10, and X9 and X10. So it seems like we have some violators here. X10 is a common violator, X1 is a common violator, X2 to some extent, X3 to some extent. So what we want to do is figure out which ones are the violators and then remove those from the analysis. Or if you have another functional form of the variable, you will want to think about throwing that in instead of how they're measured now. Just like everything else, it's up to the researcher. Like you have to sit there with the data and figure out, are these things, do they need to be in the model, or is their overlap detracting from the model? Linearity, normality, and homoscedasticity. Here's a picture of the Tabachnik and Fidel book. We can examine this one assumption of these three things with a residuals plot, plotting the y value minus the predicted y value. So this would be the predicted y value across all of the values of x. You'll notice that you're going to have a predicted y value here, and the residuals are going to be the distance between the expected y value or the actual y value and the predicted y value. The predicted y value is the line, the 0 line, and each of these dots represent the distance from that line. So you can think of like the scatter plot that we had earlier, and now all of those dots across all of the x variables are plotted this way, and they represent a distance from the line. What we want to see is something like the top left, where all of these residuals are all equally above and below the line. It doesn't seem like there's extreme curvature, right? They're equally distributed about the line. In this first one here, we see violation of normality. If the variables or the residuals are normally distributed, they should fall equally on both sides of the line. Here we see there's a hard line stop where they fall mostly below the line and then they stop at a certain distance above the line. That would indicate to us non-normality. Non-linearity is depicted in panel C here, where they're not equally about the line. We see some curvilinear relationship happening here. So here we see they're equally about the line. Here we see a curvilinear relationship. We don't want to see that. And then homoscedasticity. Homoscedasticity is the idea that the variance or variability is equal at all levels of the y value at every level of the predicted y value, we should see equal distances. But here we see there's more variability at the high level of predicted y, and most of the x values tend to cluster around the predicted y value at the low end. So we see a fanning out. When I say here, it looks like the bell of a trumpet. We don't want to see that. So here would indicate heteroscedasticity, heterogeneity of variance. So here, non-normality, non-linearity, heteroscedasticity. Null hypothesis is basically centered on each t-test. For the b, we say in the presence of the control variables, there is no relationship between x variable and the y variable in the population. The slope of b in the population should be equal to 0, or the slope of b in the population and b2 and b3 all the way through bk, that should be 0. Research hypothesis is that the slope is not equal to 0. I said earlier that when you're assessing these models, it does a separate t-test for each x variable's slope, and then it does an overall omnibus test for the overall regression model with all of those variables. This is what the t-test looks like. I'm not going to bore you with all of this, but you can take a look at it. Basically calculates variability between the b statistic and the population b estimate, which is 0, and variability in the b, so it's standard error of b. The F statistic, I said, compares a null model to our full model with all our predictors, and this is what it looks like. Another way of calculating it is using information from the R-square value. So we had the t-tests, which test the significance of our b value, our regression slopes. We have the overall omnibus F test that tells us how good our model is compared to the null model. Another F test is the F increment test, which compares any previous model to our full model. So we can do one model with nothing in it, another model with 2 variables in it, another model with 15 variables in it, another one with 50 variables in it, and we compare each of those. We can look at the change in F. But if we want to know how good a model fits, we use our R-square statistic, and each regression model is going to give us an R-square value. And similar to our correlation coefficient, when we square it, it gives us an R-square value, and that tells us the proportion of variance in Y that is explained by X, or variation in X. Here, when we run it for a regression model, a multiple regression model, R-square represents the proportion of variance in Y accounted for by the variation in all of the X's, the combined X's in that regression model. So here's an example from our book, our textbook. This is a good illustration of what goes on in the regression model. Here are some results from a multiple regression model from SPSS. So SPSS gives you a lot of stuff when you're calling the regression. Here we're looking at the relationship between 5 different variables and overall course rating. So you have 50 students giving a rating for a course overall. They were also asked to rate different things about the course. So rate the teacher, rate the exam quality, rate the teacher's knowledge of the subject material, rate your grade in the course, and rate the enrollment, or tell us how many people were enrolled in your class. So we see the correlation matrix over here. It's displayed a little bit differently from how it would in R, but here we see the overall and overall correlation. It's 1, and you'll see everything on the diagonal will be 1, and that's because when you correlate something with itself, it's a perfect correlation. It's going to be 1. Teaching and overall rating, correlation of 0.8, exam 0.59, 0.68, 0.301, negative 0.24. Significance is depicted here by the stars. We know that the stars indicate significance for all of these tests. Some of them are more significant than the others. Let's move over here. So each model, it's going to have a list of coefficients. So it's going to have my constant, which is going to be b sub 0. We're going to have our teach variable, which is x1. Our b sub 1 is 0.763, b sub 2 is 0.132, b sub 3 is 0.489, b sub 4 is negative 0.184. And we have standard errors associated with each of these b coefficients. So we can use that information and plug it into the regression equation. We would say y hat is equal to our constant, which is b sub 0, negative 1.195, plus 0.0763 times teach. So whatever somebody's rating is on teach, if it was 1 or 5 or 15, we plug that into the teach value, and it would be multiplied times our slope, 0.763. Exam is 0.132 times exam, plus 0.489, and then we say minus 0.184 times grade, and then plus 0.0005 times enroll. So those are our 5 variables, our predictors. Each b value has an associated t-test. So there's a t value for the constant, non-significant. We have a t value for teach. The significance level P is equal to 0.000, so that's less than 0.05, so that's significant. 0.81, non-significant. 3.5, significant. So we have t-tests for each of these. So it's saying, is the slope of this variable significantly different from 0? And we're finding that the slopes of teach and of knowledge are significantly different from 0. We see an overall or omnibus test. So we have the null model. So residual here would be the line for the null model. The regression model represents the regression model with all the variables in it. So we create an F statistic, and F would be equal to 27.184. So this means that the regression model with enroll, knowledge, grade, teach, and exam is significantly better than the null model with just a constant or intercept. That means that the regression model with all these variables better predicts overall score than does a model with nothing in it. Good, so we see that the overall model is better than the null model. We see that 2 of these variables are significantly related to the outcome of overall score. In looking at one of these variables, let's say this teach variable, which is significantly related to the outcome, we would say for every 1 unit increase in the teach variable, there is an expected 0.763 unit increase in overall course rating. I'll say that again. For every 1 unit increase in the teach score, there's an expected 0.763 unit increase, right? Because it's positive in the overall score. Right, we're saying how this teach variable relates to the outcome variable, the y variable of overall. Exam is not significantly related to the y variable. Grade is not, enroll is not. So we don't need to say anything about those variables because they are not significantly related to the outcome. If they're not significantly related to the outcome, there's no point in talking about how increases in that variable will lead to an increase in the y variable, because that's not true. It's not significantly related to the outcome. We can say, though, for every 1 unit increase in knowledge rating, there's an associated 0.489 unit increase in overall score. You can also use this regression equation down here and plug in values for each. If everybody got 0 on exam, 0 knowledge, 0 on grade, 0 on enroll, but they got 4 on teach, you can get to someone's predicted score based on that information. So this information is used for plugging in values to predict scores within that range. And then finally, we have the R-square value here. We have R, which is 0.869. We have R-square, which is 0.75. Now, what does that mean? That R-square value of 0.75 indicates to us that 75.5% of the variance in overall rating is explained by variability in the combination of teach score, exam scores, knowledge score, grade, and enrollment. 75.5% of the variability in overall score is explained by the combination of those 5 variables. 75%, that's a lot. That's a lot. We rarely find that much. In sociology, when we're dealing with a lot of cases and stuff and aggregate information, it's often easier to find something around the 60, 70, 80 R-square range. But in many like psych studies, and in particularly psych studies with like 50 to 100 to 200 cases, you'll find something in the range of 10% or 0.1 R-square or 0.2 R-square. And if you're around 0.25, it's like, oh my God, you've done a lot. Right? And that's because you're looking at trying to explain variability in individuals as observations. And there's so much that can account for variability at the individual level, at the micro level. And then I want to end with talking about the relative importance of predictors. So we looked at the T statistics representing the regression coefficients for each predictor. We look at them and see that they're significant, but you also might want to compare which one has more weight or more impact on change in the Y variable. So you figure out which ones are significantly related to Y. We saw in our example that teach and knowledge were significantly related to Y, but we might also want to see how much each of those influences Y, or how does one influence it more than the other. We can compare the B values, but the problem is the B values for each of these variables can be measured differently. For instance, one of the variables might be income, and it ranges from $1 to $1 million. But we have another variable called age, and it ranges from 18 to 78. Right? These are 2 different kinds of scales. So when we calculate B coefficients, they're going to be relevant for their own variables. They're not standardized across all these variables. So comparing the 2 would be like comparing apples to oranges. But to make them comparable, we have to adjust the scale, making them all similar. And we do that by standardizing these coefficients. We standardize the b-values. That is, we turn them into something like a z-score. This would convert our b to a standardized coefficient, beta, which would be in standard deviation units. So whereas the interpretation for b is for every 1 unit change in x, we see that y changes by b units. For beta, it would be for every 1 unit change in x, y changes by beta standard deviation units. And let me go back here just to show you in the regression output. We'll see this in our linear model as well. We see b for each variable. You'll see up here it says unstandardized coefficients, but we'll also see standardized coefficients. So every 1 unit increase in teach is related to a 0.763 increase in overall score. We have the standardized coefficient beta here. So for every 1 unit increase in teach, we would experience a 0.662 standard deviation unit increase in overall score. So now everything's in standard deviation units. And the same thing, you only interpret the significant ones. So teach and knowledge. This is how we calculate standardized regression coefficients. We just take the b times the standard deviation of that b divided by standard deviation of y. Next, we're going to be talking about measurement and diagnostics, so dummy variables, missingness, mediation, moderation, different types of correlations, and why multicollinearity is important to consider, as well as approaches to regression. We can do a standard entry or forced entry like we've been doing here with like 5 different variables, or we can block our models where we have 2 variables in the first model, 3 added variables in the second model, 5 added variables in the third model for a total of 10 variables. And we can see which models fit our data better. And then we'll cover statistical approaches to regression, which are never good